Okay, so we are ready to pick back up with control charts and quality control statistics. So the way this is going to work over the next few days is today I'll do section 17.2 and probably get a start on 17.3. Then Friday I'll finish it all up, and that'll be the last new material. And then Monday we'll review for the test, and the test will be Wednesday. Got it?
When are you posting the review guide?
It'll be posted by Friday. It won't be tonight. Unless I happen to have it already made out from last semester, but I don't think I do. So I think I have to create a whole new one, and that'll take a while. And I'm traveling tonight. We'll be gone all day tomorrow and not get back until late Thursday. So I'm not going to really have any time to do it. But on Friday, I can get the thing finished up and get it posted, so you'll have it over the weekend. And then Monday, we'll go over it in class. And then Wednesday, the test. All right? So then you may be thinking, so what are we going to do the rest of the semester?
Work on our project.
Projects, right? So we've got a couple of days built in as project days. Come to class and work on your project. With me there to ask questions. Right? So we'll do a couple days of that, and then we'll be presenting your oral presentations of the projects. And then whatever days we have left, we'll review for the final. It may only be one day. It may be 2 days. I'm hoping it's 2 days. All right? So this class is called Applied Statistics. So I think the projects and the presentations showing that you know how to use the statistics that you've learned to actually analyze some data, even though it's not life or death data. It's baseball, but it's data. Okay, so any questions at this point on what we've talked about so far with the quality control and control charts and all that? You haven't had any homework yet, so I'm not surprised there aren't questions. But as soon as you start working some problems, then that should generate some questions. So let's remember where we were last time. We had talked about the limits, the upper control limit and the lower control limits. And we've talked about X bar charts. Right, so X bar charts, and we talked about S charts. Right? If we have time, we'll also talk about P charts, and the P stands for proportions. So that's something where the variable you're measuring is a categorical variable, and I want to know what percent are in this category, and usually it's acceptable versus not acceptable. So you're doing quality inspections and say, hey, this one works, this one doesn't work. Right? So you want to control the proportion that work. But it's really similar stuff, so I don't have to get to it, but we do need to actually form some of these. I'm almost done talking about them, and then we'll get into SAS. We'll do some hand calculations and produce these. Right? So let's talk a little bit about setting up control charts in the beginning, and I started this discussion last time, but we'll finish it up. So we talked about monitoring past data to get estimates of mu and sigma, right? So you base those estimates on past data for when you think that the process is stable, and then we typically monitor both of these things. A lot of the software, including SAS, and I'll show you this in SAS in a minute, and a lot of the old textbooks would do, instead of X bar and S charts, they would do X bar and R charts. And the R stands for range. I'm not really going to even talk about it in this class because it's from back in the days when a lot of these calculations had to be done by hand, and the graphs were drawn by hand on graph paper. And R stands for range. And remember, range is a measure of spread or variability, just like standard deviation S is. But it's not as good a measure. But it's a whole lot easier to compute by hand. The range in the data is the maximum minus the minimum. Single number, pretty easy to compute. Whereas computing standard deviation with a handheld calculator is a little bit tricky. So people would do these R charts, but they're not as good at monitoring your process as an S chart is. So we won't even talk about it. The book talks about it just enough to tell you what it is, and then that's about it. And it says, modern software allows us to do more complicated but better X bar and S charts. So, once we have an estimate of mu and sigma, right, then we're ready to start setting up our control charts to monitor a process going forward into the future. Remember that for the mean of the process, mu, then we can have target values. And often you do, right? You have an idea of, that if I'm making ball bearings and they're supposed to be a certain diameter, then I got a target for mu. It should be that diameter, right? But for S, or for sigma, we really don't have any target. We want to keep it as small as possible, but we don't have a target that we go. So we can have targets for mu, but not sigma. So your target for mu is often where you put the center line of your control chart. I want it to vary around the target. But for S charts, we don't have that capability. And also, it's not usually possible to directly manipulate sigma. You can manipulate the mean of a process often by turning the dial on the machine or whatever, right? You can manipulate what the mean of the measurement is. But the standard deviation, the variability, is you can't directly manipulate that. You can indirectly do it by firing Bill. Remember we talked about Bill and answering the phone? Bill's not good, so we fire him, so now my standard deviation goes down. But I can't turn a dial on a machine and change the variability, right? So targets aren't always a good idea. So now we're ready to roll. So step one, based on the past data, right? So you've been collecting data for a while now, and the first thing you do is make an S chart out of that past data. So it's a good idea to begin the process by looking at variability, not the mean. Right? The mean can be okay, but if the variability is too big, then you still are out of control. Right? So then make that S chart, identify points that are beyond the limit. So you have your lower limit and your upper limit of control for your standard deviation S. Make an S chart out of the past data and identify the points that are beyond the limits. So you say, well, on this day, we had a lot of variability that day, right? And inquire, however that's done, about special causes for those points. Special causes for the reason, I guess. Special causes or reasons for these points. I wrote the word for, but I mean or. So let me erase the F. So special causes or reasons for these points. Okay? Oh, that's the day we hired Bill. Right? So our variability shot up on that day. Right? So things that cause disturbances in your normal, everyday, random variation that's common cause variability, if you've got a spike and it goes out of limits, then there's probably a special cause for that. Remember those two terms? Common cause and special cause. So we'll learn to call special causes for variability, for S charts, as S-type causes. So, and then you'll have S-type and mu-type. Right? So they affect the mean, they affect the standard deviation. Right? So then, after you've identified these points and you've come up with what you think are the reasons why those points were out of whack, then you remove those samples from the data. Remember, every value of S that you're plotting in an S chart is the standard deviation from a sample. And usually those samples have 4 or 5 items or measurements in the sample. Right? So you remove the entire sample for a value that's been identified as out of control or out of the limits. Right? So you go back and say, well, I don't want to include that in my past data because that day or that sample was odd in some way. So I don't want to include it as when I'm trying to estimate what my targets are. Right? So remove those samples and recompute sigma hat. Right? So in step 1, we had past data and we estimated what sigma hat was. We used that estimate to give us the center line of our control chart, our S chart. Right? But then all the points that were out of whack, we remove them. Now we go back and recompute. So this is kind of an iteration. Right? So we recompute sigma, sigma hat, and S bar. I haven't talked about S bar yet, but as you might suspect, that's the mean of all the S's. And remember, that's not the same as sigma hat. What did we say about the mean of all of the standard deviations? It's a biased estimate of the overall population variability. So we have one of those constants we need to multiply this by. Right? So we'll do an example of that in a minute. Then make a new S chart. All right, so we've got this iteration going on. I just hit page down. Was everybody done with writing what they needed to on the last page? I went quick there. Has everybody got what they want? Okay. It's all in the book, in case you didn't. But so step 3, after you've made this new S-bar chart, you again look at it and see if anything's out of whack. It shouldn't be now, right? Because you've removed all the ones that were out of whack before. But now you're manipulating where the center line is and the control limits and all that. So the control limits actually come down a little bit because your overall estimate of the variability has decreased, right? So there may still be another point that's out or so, but usually not. But if it is, you go through the iteration again. But once all S-type causes are removed, now you're ready to make your X-bar chart. And that's the ultimate goal, is you want to control the mean of whatever this process is. Right? So once you have variability under control, Then you're ready to look at your X bar chart. So I wrote X bar and then I wrote the word bar because I was talking. So that erase that and write the word chart, an X bar chart. Using only the good samples. What do I mean by good samples? What do you think that means? Using only the good samples. Yeah, the ones that you threw away because of their variability, you don't use them when you're estimating the mean. Right? So keep only the good samples and then use them to make an X bar chart. If there are points out, now see, so far we're still working with past data. We're getting the whole quality control system set up at this point, right? So we're getting things set up. We're looking to now go into the future monitoring the process, but I got to get a good center line and upper and lower control limits, and so that's this process. So if points are out, again, same kind of strategy. Look for reasons. And attempt to correct. Now often, he talks about this in the text. I won't write it down, but when he says attempt to correct, a lot of times this is not just the statistician working with the data. Oh, here's a bad sample, so I'm trying to get my X-bar chart set up, so let's remove that sample. But it's more like go back to the people out there on the line and say, hey, we found these points out of whack. Let's figure out what happened on those days or in those samples. And maybe it's because the machine was out of calibration. And let's get it back in calibration or whatever. You try to get those reasons fixed, right? So correct anything that you identify. And it's not going to be a single person that's doing this. This is a team effort, right? To identify things that were problems, get them fixed. Because now you're ready to start monitoring into the future. So you get anything that is not just common cause variability, get it corrected. Right? So that's the last step. Step 4. Once X bar and S charts are in control, use mu hat and sigma hat, right? So this mu hat and the sigma hat are after you've gotten everything in control. You're using only the good samples to make estimates. You get an estimate for your mean, you get an estimate for your variability, and use those to set tentative limits. And we use the word tentative just saying, you know, these things we might refine them later as we get more data. But for now, at least, we're going to start out, and these are going to be our control limits. So set tentative limits going forward. To monitor the process. Okay? So it's a pretty iterative, is that a word? Iterative process. Right? So it really is some statistical and mathematical, just looking at numbers in a data file, and some going out and actually talking to the people that are working on the process and figuring out, you know, what's going on here? How come this one's out of whack, and getting that fixed? So some of it's data, some of it's real life. Yeah?
So all this is to set your baseline of what's acceptable?
That's exactly right. Once we finish step 4, now we have a control chart with lines on it but no data, and we start collecting data into the future and monitor the process. Now, maybe over time we start to think, you know what, our estimate of mu is a little bit off. It's too high or it's too low, and there may be reasons to move that, or the target gets moved or something. So that's why the word tentative is used, but this is at least your starting point. Okay, so now before we start working with some example data here, a couple more things to look at. There are what we call rules for alerts, right? So what do we mean by an alert? Well, that's when you flag a point, go, ooh, something bad's going on, you know, the alarm goes off kind of thing, right? So we need to talk about the different rules for doing that. I want to pull up the definitions as they're shown in the book, because they have some pictures of this, but there's basically two of them. One is 1 point out rule, or single point out. So if it goes beyond the limits, you mark an X on it. We talked about that last time. And then the run rule. Okay, so a run rule, and I talked a little bit about this before, but I'll firm it up today. A run rule is where you have a certain number of points in a row that, even though they're maybe within limits, they're all above the mean, or they're all below the mean, and you say, hey, it looks like we're drifting, you know, and you haven't drifted clear out of the limits yet, but you're heading in that direction, so why wait, right? If it's pretty clear that things are getting out of whack, if you use the run rule, you can stop the process and fix it sooner than waiting till a point finally goes out above the limit. So you use a combination of these two things. You use both of these rules at the same time, I guess is what I want to say. Okay? Before I write down why we use the run rule, yeah, here we go. 1 point out rule and the run rule. It says the X-bar chart shows 9 consecutive points above the center line or 9 consecutive points below the center line, then that's a signal that something's bad. So when we see the 9th point of a run all above the center line or all below the center line, then that's a flag for an out of control process. All right, so my thumb never seems to work, so let me scroll with the mouse. All right. So look at this chart. This is an X-bar chart. They're plotting the means. We've got the lower limit and the upper limit as the dotted lines. And right here, it crosses across the center line. And we've got 1, 2, 3, 4, 5, 6, 7, 8, 9 points in a row that are above the center line. And you can see there's drift to this thing, right? So that one gets flagged. Oh, thought I could draw on it. But that one gets flagged before the next point actually went out in this particular example. But it might not. You know, the next one you might drift along for another 3 or 4 times before you actually get a point out. So if you're only using the 1 point out rule, you wouldn't stop it till here. Here you stop at one sooner. Okay? Now, where did this rule of 9 in a row come from? And it always is 9 in a row. So let's talk about that a little bit. Why do you suppose 9 in a row? Nine in a row, either above or below the center line. That's exactly right. Statistically significant. So, wait, now what does that mean? Statistically significant. Well, statisticians, we all think in terms of probabilities, right? When we say statistically significant, we've computed a p-value. P stands for probability. So everything is in terms of probability. Like, if the null is true, well, in this case, we don't really have hypotheses we're testing, but you can think of it that way. The null hypothesis would be, yeah, everything's fine. Nothing going on, no problems, right? And then if that's true, what's the probability of 9 in a row, let's say above the center line at CL? Well, we can actually compute this probability. I know you're thinking, how would I compute that? But if the process is in control, so if the null is true, if in control, then you should have random fluctuation around the center line, right? So what percent should be above and which percent should be below? About 50-50. So the probability of 1 above center line is 1/2. Right? So what's the probability of 9 in a row above the center line? 9 of those. 1/2 to the 9th power. So this is equal to 1/2 to the 9th power. Okay, now I can do that. That's 1/512, which is about 2 in 1,000. You with me? So now the rule, though, doesn't say above. It says 9 in a row, either above or below. So this is the probability of being above. So you get the same probability for being below. So you have plus another 2/1,000. And that gives you 4/1,000, basically, as the probability of getting 9 in a row. All right? So 4 in 1,000. So 0.004. Well, what's the probability of 1 point out, given that it's actually in control? How often does a point, just by random chance, blip above or below the upper limit and lower limit? How often would that happen? Well, remember how those limits are set? How many standard deviations?
So 0.3%.
That's right. 0.3% chance. And where'd you get that? Empirical rule. So 1 point out means it has to be more than 3 standard deviations away from the mean. Right? So 1 point out, that probability is 1 minus 0.997. Now if you're thinking, where in the heck did 0.997 come from? That's the empirical rule. Right? So the empirical rule says 99.7% of the population, or of the values, should be within 3 standard deviations of the mean. So being outside of that is 1 minus 0.997, or 0.003, which is about 3 in 1,000. So only about 3 out of every 1,000 points would go outside the limits if it's really in control. So the other one was 2 out of 1,000 plus to be above, or to be above the center line, and then 2 out of 1,000 to be below. So about 4 in 1,000, 4 in 1,000, 3 in 1,000. Comparing those two numbers, those are pretty similar. So that's where they got 9 in a row. They wanted to get the chance of a false alarm down to about what it is for your upper and lower control limits. Right? So if you went 10 in a row, it wouldn't happen often enough. If you went 8 in a row, it'd be a little too often. Why would we not want it to be too often? I mean, this doesn't seem like these are really low probabilities. What are we trying to control for here? Why do we want these probabilities to be so low?
There's less durability.
It's not a variability issue so much, right? All these calculations are done assuming the null is true. So assume the process is working fine. It's in control. But if you get a point out while it's in control, what are you going to say?
There's the tendency to stop the process, so to speak, and if you do that, you hurt productivity
exactly.
over a long period of time.
Yeah. It's the cost of a false alarm. That's why they're controlling false alarms. These are the probabilities of false alarms. So it's like your alpha level in a hypothesis test. If the null is really true, what's the probability you make a type 1 error? That's called a false positive. So 1 point out when it's really in control, that's a false positive. You sound the alarm, they shut the presses down, they go in, they start trying to figure out which machine's out of calibration or whatever, and it's lost production. There's really nothing wrong, so they want that to be really low probability. So 9 in a row, if it happens 9 in a row, the chance of that happening, if it's really still in control, is really low probability. But 8 in a row is not quite low enough probability, so you're just setting the balance point. Right? Yeah?
Is there a connection between 9 in a row and 1 point out?
Yeah, this is the connection.
I mean, on that chart, it could have, instead of going above, it could have just gone back down and resumed normal. Does 9 in a row imply that you're going to violate one of your control limits?
No. The discussion is 9 in a row. 9 in a row should not happen more than 4 out of every 1,000 times if you're still in control. So if it's going to go back down and you're fine, you'd only get 9 in a row only about 4 out of every 1,000 points. Right? And so it's just 9 was chosen because it makes
I got
these
that.
two probabilities, they're both really rare.
So
right?
if it goes back down, you would say it would probably be in control if it didn't go outside of the control limit.
Right.
Okay.
Yeah. But you're going to stop it. If you hit 9 in a row, you're going to stop it and figure out what's wrong, because the chances that it does come back down are only 4 in 1,000. Right? The chance, now technically that's an incorrect statement, but that's the chance the null is true. If I've seen 9 in a row, what's the chance that it's still in control? Not very good. So stop it and fix it. Right? It could be okay because 9 in a row, if you flip a coin, you flip it enough, pretty soon you'll have a run of 9 heads in a row. But only about 4 times out of 1,000, if you flip it, a large number of times, only about 4 in 1,000 times would you get that.
So all of these are assuming that you have to control for both an upper and a lower limit, right? Like there would be examples like with fishing barges where if you catch more than the regular, that's fine, so you wouldn't have to control for that, right?
Right, that's true. There are processes where being off in one direction is not bad, but being off in the other direction is bad. Right? But okay. So we very much want to avoid false alarms. So, sometimes quality control processes, they'll want to add additional rules. And that's fine, but remember, any other rule that you put in there adds to these probabilities. You have a chance of a false alarm, you Well, and we're also going to stop it if, if I see one that's, the wrong color or, something, well, that's fine, but you want to only add more rules in situations that are well known. So only add additional, and I'll say ad hoc, additional ad hoc rules if process is well known and you know you kind of have a sense of what the false alarm rate would be. You may not be able to actually calculate it, but you say, well, that's only going to happen once in 1,000 times. So if you have good information about that, then it's okay maybe to add additional rules. I should have had the word well in there. It's well known. So that tailor-made rules make sense. Tailor-made rules can be devised. In applied statistics, there's always a balance between what the books say to do with the data and what common sense says to do with the data. So there's a balance here, and that's what they're trying to say is, you got this 1 point out rule, you got the runs rule, but, there may be certain situations where that if I see this, that tells me something's wrong, and I want to stop and fix it. Well, those are tailor-made or rules specific to that particular industry or process. You want to take action, even though the statistics maybe aren't telling you that you should take action. Right? But the point the author's making is just be careful. You add too many of those things, and now you got high probabilities of false alarms, and you're always shutting the process down, and you're losing production. Okay, so let's start looking at some numbers here. I want to go to SAS. I was trying to run something before class, and I ran out of time, but I want to show you how to use SAS to do this. We're going to look at Excel first, but I got an error message here. The values of the subgroup variable day are not sorted in increasing order. So I thought, well, that's a good place to stop and say, okay, you always got to monitor your log window, look for errors, and now how do I sort the data? Right? Because SAS will do all that for you. Right? So let's look at the book. Oh yeah, I got to get back to the. I have to bounce between two machines, the WooStat server and the PC here. Excuse me. And what I want to do is look at a specific exercise. He has a couple of examples in the text. So here you're seeing numbers plugged into the formulas and coming up with limits. So follow those examples through as well. So I don't want to do that example because you can look at that yourself. So I'm going to go to the homework and pick one and do it as another example for you. Right? So this one is, this is the last edition of the book. This same problem is in your new edition of the book. It just has a different number. I think it's 44 now, and in this one it's 38. But so 38. I'll read it, and then this is the table of data. So I'll scroll back up so we can look at it. But what it is monitoring the calibration of a densitometer. So this is a medical device that measures the bone density in patients. Right? So have you heard of osteoporosis? Right? So that's where the bones start to thin. Well, they measure that with a special machine, but that machine can get out of calibration. And then If it gets out of calibration, then you're telling somebody they got osteoporosis when maybe they really don't. So you need a control process to make sure that it gets recalibrated every so often. So you can think of the runs rule here as being real important. When things go out of calibration, it's usually not a sudden boom, they're done. It's more of a drift. So as things start to drift, you'll start to see runs that go above the mean. Right? So loss of bone density, serious health problem, blah, blah, blah. Control charts based on these measurements. So I need to read a little bit up here. The manufacturer supplies a phantom, which is an aluminum piece of known density that can be used to keep the machine calibrated. So even your scale at the doctor's office, they recalibrate that every once in a while. They've got the same metal weight that has a known weight, and they set it on there and see if it's measuring the right weight. And then if the scale gets off, they may have to turn the dial a little bit, right? So that's the same idea here. So it's this big chunk of aluminum. They know the density, so they can measure the density, see if it's getting the right reading. All right? So each morning, the clinic makes 2 measurements on the phantom before measuring the first patient. So they do this every day, right? So what's their in here? 2. Right? You say usually it's 4 or 5, but in this particular problem, it's only 2. So N is a 2. So each day, they take this sample, this quality control sample of size 2. They measure the density of this aluminum chunk, and if they're in control, then they start measuring patients with it. But if it seems to be out of control, then they stop, they recalibrate their machine before they start measuring patients. Okay? So the units are in grams per square centimeter, and then there's different parts of things you're supposed to do here, but I'm going to kind of dispense with that, and we're going to make these charts, right? And I'm not going to have time to get the whole chart made, but let's do a little bit by hand so you can see the process. So here's the data file, and this is in an Excel spreadsheet. So you have day, and they have 30 days worth of data here, right? And each day they have 2 measurements. So and all their data in this textbook is set up the same way, and unfortunately it's not the way SAS wants it read, so you're going to have to manipulate the data a little bit when we do a homework problem. But we got 2 readings. So on day 1 we have 1.261 and 1.260 for an X bar of 1.2605 and an S of 0.000707. Okay? See what we're doing? So this is standard deviation of just 2 measurements. And you can kind of look down through here and see that they're pretty stable, right? It's always 1.26 something. Once in a while there's a 5, but what would the first step be? Look back at those steps that we said. Look at this past data and use it to estimate mu and sigma, right? So I have already, let me go back to the other machine and pull up the Excel spreadsheet that has that same data, right? So here's the data, okay? So what is your best estimate of mu?
The weight of the thing they're weighing. The weight of the known object. Or, I'm sorry, the density.
Okay, that's going to be your target value, right? So that's exactly right. We know this aluminum chunk that they're measuring has a known density. So that's definitely your target, right? You want your sample means to hover right around that, right? Now, did I miss it in the reading? Did it say what the known density was? It looks like it's about 1.26, but everything's a little bit higher than that here for means. So I didn't pay attention, but that's your target. but we want to estimate the mean of our process. So what's our best estimate of that? What'd you say?
1.26.
Is that what it said? But
bar. The average.
X bar bar. That's what I was trying to get somebody to say. So I can't draw on that yet, right? So let me I want to go back to my note sheet here and say, let me get a new page. Mu hat is equal to X bar bar. 2 bars above it. And so what do the 2 bars indicate?
Average of the average.
The average of the averages. Right? So it's the mean of the sample means X bar. Right? So you have that column of sample means. You take the mean of that, and that's your X bar. Okay, so let me flip back over there, and I'm going to use Excel to tell us what that value is. Now Excel, the newer versions of Excel, this is pretty nice. All I got to do is drag across that column, and down here at the bottom it says average is 1.2619. But I could also use my means function, or the average function. So I'll do that. If I click this auto sum button, after I've dragged across and highlighted the cells I want the average of, you click on this auto sum and it'll give you the sum or the average or the count or the max or the min, right? So it'll do any of those things you want. So I want the average, so I'm going to click average, and then down at the bottom it would have added another value. So that is my X bar bar. Okay? And doggone it, I'm out of time. But now S bar, same thing. So let me just do that real quick. I'm going to drag across all the standard deviations and hit auto sum average, and I get 0.002805. Right? So this is X bar bar. That's your estimate of mu. This is S bar. It only has 1 bar on it because all of these S's don't have bars. You see why the notation gets a little cumbersome. But so this is not an estimate of sigma, though, is it? Because remember, that's a biased estimate. So we need to multiply that by one of those C constants. So I have to do that on Friday. All right. So you'll look up in Table 2 in the book, see what the constant is for samples of size 2 to multiply that by to correct for the bias. And then you have an estimate of sigma. All right. So we'll see you then.